In this segment, we're going to be talking about phase and how pressure, specific volume, and temperature are related to one another. So you've probably got a good idea about the three phases of matter, and you've also probably got a good idea of what's going on with the molecules within each of those phases. So as you move from a solid to a liquid to a gas, the microscopic energy is increasing and the distance between those molecules is increasing as well. We'll talk about phase changes a lot in this class, and we'll focus primarily on the phase changes from a liquid to a gas or vice versa. So evaporation and condensation. Now when you've got a liquid, you've got one phase. When you've got a gas, you've got one phase. But if you're going through a phase transition, so evaporation or condensation, you've got two phases present. You've got liquid and gas, so two phases. And that's going to be important to remember. Now, pressure and specific volume and temperature are all related to one another. And it's going to be, the relationship between those things is going to be dependent on what phase you're in. So what you see in the picture here, you've got a 3D representation of how all those things are related to one another. And this will look a little bit different depending on what substance you've got. I believe this one is for water. And there's a lot of information here, but what I want to draw your attention to specifically is that liquid vapor dome shaped thing in the middle. So within that dome, that orange dome that you see there, you've got a substance, and it exists in two phases. It exists in the liquid phase and the gas phase. So gas and vapor are two terms that are synonymous in this class. So in other words, it's going through a phase change, either condensation or evaporation. It's a little bit difficult to pull any meaningful information off of this 3D information, especially in a 2D format. So what we're going to do is we're going to project this onto a surface. Let's look at a PV diagram. So what I've drawn here, you've got your liquid vapor dome. If your substance is on the left-hand side at those particular pressure and specific volume coordinates, if you will, then you have a compressed liquid or a subcooled liquid or just a liquid. Okay, so all three of those things mean the exact same thing. We have two fancy terms for a liquid. I usually say compressed liquid. If you're underneath that dome, this is the two-phase region here called the liquid vapor dome, the region of saturation. So you've got two phases present. You've got liquid, and you've got vapor. And if you have a substance underneath that dome, you might just say that it's saturated. If you're to the right of that dome, this is a superheated vapor or a gas. Both terms mean the exact same thing. We just typically say superheated vapor in this class. Now, we've talked about what happens if you're on either side of the dome or if you're underneath the dome, but what if you're actually on the dome itself? Well, if you're on the left-hand side, the blue line that I've drawn here, that blue line corresponds to what's called the saturated liquid line. And if you're on that line, you have a saturated liquid. So saturated liquid is still all liquid, but it's on the tipping point and it's about to boil. So if we move into that two-phase region at all, you'll start to see gas bubbles form. If you're on the right-hand side, the line that I've drawn in red, this is your saturated vapor line. And a saturated vapor, still all gas, but it's about to condense. So if you move anywhere to the left, then you'll start to see condensation. You'll start to see liquid water droplet formation, or, well, I say liquid water. This could be true for any substance that you have. You'll notice that the pictures, the little piston cylinder pictures showing what's actually physically going on, it refers to water, and that's just because we work with water a lot in this class. But these relationships could be true for any substance. We could just as well say, I don't know, liquid nitrogen, for example. It would be the same relationships. All right, so underneath that dome, we said that we have two phases. We've got liquid and we've got vapor. And we specifically have a mixture of saturated liquid, which is about to boil, and saturated vapor, which is about to condense. So it's still liquid and vapor, but we specifically say that it's saturated liquid and saturated vapor. And you'll see why it's important to make that distinction as we go on in the class. Now remember, we got all this information from that 3D representation. So there's still temperature data there. Didn't just go away. So what we're going to do is we're going to sort of overlay that temperature data into this PV diagram. I can draw a line of constant temperature, and the way that it goes, start off in the saturated or in the compressed region, and that line goes down. So anywhere along that blue line, we're at some temperature T1. If we move along a line of constant temperature T1 into that two-phase region, you'll notice that it switches direction. So what you see is that in the two-phase region, if your temperature is constant, that pressure is constant as well. The same cannot be said in the compressed region, and it also cannot be said in the superheated region. So the temperature continues, well, it's constant, but the line goes down, right? We could also draw another line of constant temperature. So I'm just picking arbitrary locations. I'm calling this T1 and T2, and the direction of increasing temperature goes in the direction that you would think it would go. So T2 is greater than T1 in this picture. And like I said, if you're in that two-phase region, if your temperature is constant, pressure is constant too, and vice versa. Let's look at that T1 line here. So at T1, if you're at T1 and you're saturated, you're in that two-phase region, there is only one possible pressure that you could be at, and that's P1, and vice versa. If you're at P1 and you're two-phase, the only possible temperature that you could be at is T1, okay? So we give that a special name. We say that that line T1 is the saturation temperature at P1, or sometimes we shorthand it and say Tsat at P1. All right, now let's look at a TV diagram. So you'll notice that this is another projection from that 3D representation onto a surface. You'll notice that the shape of the dome is just slightly different. It's a little bit taller, a little bit skinnier. I'm not a great artist, so in class you'll probably notice that my domes on a PV and a TV diagram probably look pretty similar. And that's just because I'm not a great artist. So if you're not a great artist either, I'm not going to take off points because I think, well, your TV diagram dome doesn't look as skinny as it should, right? As long as you draw a dome, that's fine with me. All right, so those regions that we talked about on a PV diagram, same with a TV diagram. So the left-hand side, if you're on the left-hand side of the dome, you've got a compressed liquid. If you're underneath the dome, you got two phases, you got liquid and vapor. If you're on the right-hand side of the dome, you have a gas, a superheated vapor. If you're on the dome, on the left-hand side, if you're on that saturated liquid line, you got a saturated liquid. If you're on the right-hand side of that dome, if you're on the saturated liquid line, you have a saturated vapor, which is about to condense. And if you're underneath the dome, you've got a mixture of both saturated liquid and saturated vapor. So same concepts. If you understand a PV diagram, you understand a TV diagram. We can also overlay pressure data here. So let's draw a line of constant pressure here. All right, so there's a line of constant pressure, and you'll see that it goes the opposite direction of the line of constant temperature on a PV diagram. So in the compressed region, it's kind of going up. Remember, the pressure is constant, but the direction is up. So along that line of constant pressure, we go up in temperature, and then we go into the two-phase region. And just like we saw on that PV diagram, if our temperature is constant, our pressure is constant. So here we are, our pressure is constant, and we see that our temperature is constant as well. And then the line goes up, continues to go up in the superheated region. So anywhere along that blue line, we have a constant pressure of P1. So you'll notice it looks pretty similar to that line of constant temperature on a PV diagram. It's just the ends are flipped, right? And I could draw another line of constant pressure. I'm going to call that P2. And the direction of increasing pressure goes exactly the way you would think. So P2 is greater than P1. Like I said, in that two-phase region, if your temperature is constant, your pressure is constant. Vice versa, if your pressure is constant, your temperature is constant in that two-phase region. And we can refer to the saturation pressure or temperature here as well. So we're going to, at a given T1, if you're in that two-phase region, there's only one possible pressure you could be at, which is P1, and vice versa, just like we said when we talked about the PV diagram. If you're at P1, the only possible temperature you could be at is T1 if you're two-phase, and we give it a special name. We say that P1 is the saturation pressure at T1, or we call it Psat at T1. And we could switch it up. We could say, well, T1 is the saturation temperature at P1, vice versa. It doesn't really matter. It's two ways of referring to the exact same thing. All right. Well, that's it. I hope that was helpful.